because of their form and their simplicity. Canonical is a good word. If something is called canonical, it's very good. Okay. So let's plug that in to here. Okay. And that gives you. And you're going to notice the symmetry that's inherent in this definition. We just swap the differentiation variables. Okay. Now we're going to define this algebraic quantity as something called the Poisson bracket, and it's going to be denoted by square bracket with the Hamiltonian and the dynamical function. So finally, we get for the time evolution of any dynamical function that is dependent on the coordinate and momentum, it's going to be governed by this equation, and we can say that this is the equation of motion for this dynamical function. Okay, and so in a sense, you can see that it is the Hamiltonian that governs time evolution in classical mechanics. Okay, and in quantum mechanics, you will see a very close analog of this. So you just saw the Schrodinger equation. There is also a different, there's an equivalent way of doing quantum mechanics based on the Heisenberg equation, and this in every way looks like the Heisenberg equation. Okay. So this is our overview of classical mechanics. There's actually no need for you to go back and if you don't know these, this knowledge is enough. You don't need to actually go and study classical mechanics because you're studying quantum mechanics here, and classical mechanics is just one of its limits. There are no way to derive quantum mechanics from classical mechanics, and you can only go the other way. All right? So.
You want to derive those canonical equations, just present them, right?
Right. No.
Canonical equations, did you derive them?
Yes. I mean, once we write down this, EH is equal to, what was it? The things I just erased there, right? So there was Pi dot dQi. And then there's a minus sign and the plus the qi dot dqi. Once we derive this from the Lagrangian, we can just read off these equations. Because that is how
when you show us where you get this equation.
That is how the partial derivatives are defined.
So then how do you go back to just the Hamiltonian with these things?
Okay, so let's say that the Hamiltonian is only dependent on the the momentum and the coordinate. Then these two equations completely specify the how you take the partial derivative of the Hamiltonian. So you can construct the total derivative of the Hamiltonian. From these equations, you will write that the total derivative is going to be equal to. Okay. Now. Okay, and then you just plug in the canonical equation and you get this.
No, but you have to show that from that equation. Second line on the right.
This?
Yeah, you have to show that to there before you make the connection.
Isn't that what I did over here? Maybe I should just go over it once again. Maybe.
Does everybody catch what I am saying? You know, where the two canonical equations come from?
To do this, okay, you construct the total derivative of the Lagrangian. Okay, and then you do a chain rule to bring this term out. Okay. And then you construct a new quantity, which is the difference between this and the Lagrangian. Okay. And you have constructed its total derivative. So once you know the total derivative in this form, you can read off the partial derivatives from here, because this is the definition of partial derivative, right? And that gives you the canonical equation.
But then aren't you, but then I guess what he was trying to say, because it seems like you're already using the definition to define itself, so.
This definition is not part of classical mechanics. This is how.
That last line is calculus. That
Yeah.
second last line comes from somewhere else.
This comes from,
Come from
okay.
that equation, right? But you
Yeah.
never show where the second last line comes from.
I did over here.
No, you didn't show it, you just put that line that you went to on the top.
No, okay, you can check the video. I did it. No, seriously, I did it. All right, so I guess we dismissed them.
Yeah, we can. If next time you come at 9 o'clock.